Thanks for coming, guys. Hope you haven't heard too much about Scale over the last 2 or 3 days, but it's a pretty popular topic. I find it extremely interesting myself. My name is Jeremy Eder. I work for Red Hat currently, and I co-lead a team of performance and scalability engineers. We're currently working on OpenShift. The larger team at Red Hat works on covers performance and scale for every Red Hat product. So it's a fairly large team. Today we're going to talk about some work we did in late summer on the CNCF lab to scale test Red Hat's enterprise-ready distribution of Kubernetes, which is called OpenShift. And I did a talk at LinuxCon about workload classification as well. So I'm going to try and bring in some of the performance aspects, which is my traditional background, is making workloads go fast. I'll share some of what we're working on today. And when I say we, I mean I co-lead the team with Tim Sinclair, who's somewhere, hopefully in the room. And he's the best. And then, then we'll go through some details about the lab work that we did. And if all goes well, I'll show you a quick demo of some work we're doing in the context of SIG scale to more formally define what scale actually means. So this is our group in kind of a simple workflow. We take inputs from the field. We might get requirements from customers or potential customers about what they need the product to do. And we'll try and make sure that that occurs, that can work correctly and is properly supported. We do upstream development. We do test execution and design of test plans. And we work very closely with the quality engineering team at Red Hat to ensure that they run these things formally in regression test plans. So we feel like we've got decent coverage, and we can always do better. And one of the things I'd like to hear from you guys today is, what does scale mean to you, and what does performance mean to you? So if any of these slides if you have any comments about these slides, please just shout. Oh, and there's a link. I'll put these slides on SlideShare afterwards or on Twitter, but there's a hyperlink here to our Trello board, which is public. All of Red Hat OpenShift Engineering's Trello boards, so our Agile workflow backlogs, are on Trello and publicly available, so you can see exactly what we're doing. Listen to your app. So here, we'll do a couple slides on performance. People ask Red Hat, how do I optimize my environment? Premature optimization is usually not a good idea. But we do try and make the best guesses that are generally applicable to most workloads. That's actually part of what we want to do for what does scale mean in Kubernetes, is widen the workloads that run in that test plan to include things that customers might use. And so who here today is using Kubernetes? Who's using more than a 100-node cluster of Kubernetes? Do you work for Google? Yeah, OK. So anyone running 100 nodes or more that isn't doing like research and development? OK. So the scale guys want to do significant scale, and rightfully so. We want these huge environments. We have these ideas, grandiose ideas of what is really cool and sexy to work on. But I just want to temper that with some reality here. And the applications that are currently running and that Kubernetes is designed to run are web applications. And incidentally, if you're interested in running non-web applications, high-performance applications, things that don't use Ethernet perhaps, or IP, come see me after the talk. There's some potential there to expand what Kubernetes can do right now. So this slide goes in every deck that I do. It's a food group analogy slide. I want to give you guys a sense of how I characterize a workload when it comes to me. For example, if a new application is under development at Red Hat and they say, performance engineering guys, you need to take a look at this and tell us if our architecture is sound or not. These are some of the things that we look at. These are 4 food groups of performance. Every application can be decomposed into these resources, and then you further optimize into each resource. I've heard some really interesting stuff in the CPU space about proactively monitoring in like cycles per instruction on Google's cloud, et cetera. I think that's some pretty sexy stuff. But these are things we do internally, and this is kind of how these things need to be in a healthy balance. If any one of them is contended, your application is not going to perform correctly. So here with my enterprise and Red hat on, there's some additional concerns that you might have outside of the performance realm that are equal or even more important than the actual performance. And these are things that we take extremely seriously at Red Hat, and this is why we call ourselves enterprise. The things like support and security we take extremely seriously. Part of our major contributions to Kubernetes have been in this area. And of course, stability, reliability, bug fixing, being able to pick up the phone and call someone, et cetera. So take the Red Hat corporate hat off for a minute. Decomposing a particular workload. Let's say we have a build farm. Red Hat has decided to compose all of our containers that we ship to customers using OpenShift. So we use OpenShift as a build farm internally to compose, like if you do Docker pull rel 7 or whatever, you get an image that was run through this OpenShift-based build farm. And this is publicly open source, publicly available, of course, like everything we do. So we did some work on optimizing that environment. We found issues with Docker not being parallel safe for builds, for example, running into I/O contention. And some of it was learning how much I/O does it actually take to do a build? Is there more optimal ways? Can we do some caching to shield the storage subsystem from having to do repetitive I/O? And we also had to implement some queues in front of the actual Docker processes so that we wouldn't flood the Docker API. I think about all of these kinds of things when I'm characterizing a workload. And so as you look at this slide, think to yourself, what does my application look like on this chart? Do you need live migration? Does it run Windows? These are things you would want to know about your app. Obviously, you know these things about your application. And what level, you modulate the level of concern. That's what the left side means and what these icons mean. Incidentally, an hour-long talk on this topic is already on SlideShare if you just search for my name. But in this case, a build farm isn't necessarily sensitive to network latency, but it is sensitive to network throughput because I'm doing pushes and pulls, and maybe I'm getting stuff from Yum or wherever else to actually compose my container. So these are the types of things that I keep in the back of my head. And at least from my point of view, the only thing that matters is making your apps run well. So that's kind of the performance side of it. Does that make sense? Does that methodology ring true at all? Who can give me one example of an application that's not a web-based application that they want to run on Kube?
Rendering for VFX.
Awesome. So do you use GPUs for that?
Sometimes.
Yeah. That's right up my alley. And I believe we will do something with that. I hope we can do something with that. Red Hat's perspective, standardize everything. The value of DevOps cannot be realized without portability and a standardization of at least the container image format. We're not going to be able to build a successful ecosystem of ISVs, software ISVs, around Kubernetes and the container platform without some sort of standardization. They're not going to run and do, we know these Java, like if you're selling a Java app, you deploy it as, like you sell it as a zip file. You don't package it as a deb or an RPM. So the idea being there was no portability at the time when we were doing these package managers for the last 20 years. We hope that the container image format can solve that. And incidentally, Red Hat plays somewhat of a role in both of these consortia, or at least I would call them foundations. So what do we do that's different than what or in addition to what the Kubernetes and community do for scale testing of OpenShift, of Kubernetes? Back to the word enterprise. So you have Kubernetes. What else do you need to make it actually work? You need things like a registry. You need an SDN. You need some sort of storage on it as well. So these are things that Red Hat sells additional products for, and these are types of things that we are going to add on top of the normal Kubernetes scale tests. So we're going to do, build performance. I mentioned the render or the build farm earlier. We're going to do registry scalability, logging and metrics, OpenShift has like an EFK stack, so we use FluentD, which I noticed was just accepted into CNCF. So all of those things are in our realm that aren't necessarily part of the base Kube distribution, but that you get when you purchase a distribution of Kubernetes from an enterprise vendor. So on to the actual lab tests. In I guess May or something, we found out about this cluster, and they were allocated 300 nodes on it. And because we had a goal of a 1,000 node Kubernetes cluster on this lab, you might have seen this blog, but it's on the CNCF blog. But since we were only allocated 300 of those nodes, we had to do some sort of virtualization, which was not in our original plan. We decided to put OpenStack on there, Red Hat's OpenStack distribution, which was, I think, version 8, so like Liberty, if you're familiar with the code names. And so that was our cloud infrastructure on the CNCF lab. The point of the exercise was to push it till it breaks, which is every performance engineer's favorite thing to do, is to find the failure scenarios. And we also wanted to come up with a reference design, which we've done, around a scalable Kubernetes environment that is also highly available. So we put together a list of best practices out of this. We filed 30+ bugs in different scenarios. Certain things are fixed. Certain things are still underway. Certain things are just the nature of Kubernetes. So I mentioned not only do we file these issues, but like Tim and some of his guys will work with the upstream SIGs to actually fix them. If you haven't seen, the CNCF cluster is a pretty sexy resource. I think there's 500 of these nodes now, with 500 more coming online real soon. And what's cool about these nodes, and we took advantage of, was that each node has this is donated to it by Intel, by the way, to the CNCF. Anyway, each node has an NVMe device in it, which is extremely hard to come by. And if you're to try to do that on a public cloud provider, they don't offer those things yet. And even if they did, it would be insanely expensive. So one cool thing about this lab is you get really high-end stuff at zero cost. I guess if I had a want for this thing, they'd have more RAM and they'd have 40 gig NICs. But other than that, it's like, gift horse in the mouth type of thing. If you want to schedule yourself on this lab, there's a FIFO queue that's managed in GitHub/CNCF/cluster if you want to apply for it. And incidentally, I'll go through some of our next, like what's next in a minute, but we're going to get on this lab again at some point. So once we were on the lab, this is what we built. And the aspect ratio makes this diagram look really horrible. But I mean, obviously we use Red Hat's product stack, but really the architecture diagram is what I wanted to point out here. We did the whole thing highly available, so there's no single point of failure. One thing that's actually missing from this diagram is a load balancer that goes in front of the master, the API servers. So we've got 3 API servers in this scenario, 1 load balancer VM, and the kubelets talk to the load balancer. A 3-node etcd cluster, routers, registries, and 1,000 VMs. The VM, if you're interested, the VM config's down here below, but it's not really that important. So yeah, so that's what we built. And that ended up being fed into, parts of it were fed into a recent reference architecture document that Red Hat's put out, how to run OpenShift on top of OpenStack. We've also there's 4 of them, how to run OpenShift on OpenStack, on VMware, on GCE, and on AWS. They just came out this week. So you'll be able to see the very latest and greatest from exercises like this and our counterpart in my team and system design and engineering group that builds the reference architectures. So if you go to access.redhat.com, you'll be able to find these reference architectures. Okay, so we've got this environment built out, which was its own set of hilarious jokes. But after it was up and running, like I was at Marek's talk yesterday, and he had this picture of a nuke, and it really is that. We kind of call ourselves crawling over broken glass as a service. It's all, and the idea is that is what we want to do. That's what we get paid for. The idea is that after we're done crawling and after we're done being abused, the products are so much better. We have we have products that have run the full gamut of some pretty hardcore tests. I mean, like I said, we can always do better, and we will. But we feel like we have a decent mix. And here's what we have. If you go to GitHub OpenShift SVT, you'll find our repository of tests. And I'm hopeful, and none of this has been negotiated, but my personal hope is that we can port all of this stuff into upstream Kubernetes, and that we would pick and choose pieces of it potentially to use in this scalability definition. Ultimately, we would want to gate merges on scale tests if we had infinite budget, so I don't know if that'll ever happen. But I think we can do something with like mocking large environments and maybe learn a lot more. I know that's what, there's a tool called KubeMark which does that right now. Anyway, so I think the this repo here currently has a couple of network tests in it from the Google guys. We've got this weird scenario where we're trying to use who's familiar with the Kubernetes Test Harness called ETE? The ETE Test Harness currently doesn't support being accessed from outside the ETE. And so we've got just a branch down here until the SIG testing guys can figure out how to let us access ETE from outside ETE, or we re-implement the features of ETE that we're actually using in this tool called Cluster Loader, which is our main utility. So we've also got things like reliability and longevity testing where we'll run for a couple of weeks and make sure we don't have any memory leaks, et cetera. These are things to kind of harden the environment, and we've found some leaks, in fact. So I think that's all pretty cool. I think, so cluster loader is part one, and I'll go through it in a minute, and then the other piece is after the cluster's up and running, we need to fire a bunch of load at it and then see if it can really perform the way we expect it to at scale, so performance at scale. When we were building this environment, I think the first step to doing it was we need to go to an image-based deployment model. If you're scaling to 1,000, you can't have each VM go out to the registry and pull the 15 containers it takes to actually make things work. And you'd also want to we'd also want to have updates baked in, et cetera. So we built out a bunch of Ansible to do this, and it will spit out a QCow, which we used on OpenStack and continue to use on OpenStack, or Rev. And it will also spit out potentially an AMI. So it will go out to Amazon, create an instance, do the whole thing, and then the AMI will be available for us to use. I think the main steps I mentioned to you earlier, we do some file system juggling like partition resizing, et cetera. And then we do make sure we have all the updates and containers pre-pulled, and then we actually load the RPMs as well onto the system so that everything, as much as we can, is preloaded. And those are big wins, because otherwise we couldn't do the full scale. It would take forever. We use these images, and we can do massive installs of OpenShift really quickly. And that helps because we felt like we learned that we had to be capable of that because we knew we started to have to iterate a lot and do these installs over and over and over again. So the cluster loader itself takes a YAML config like this. And these templates are somewhat controversial right now. But essentially, it can take a number of projects or namespaces, which are tenants in OpenShift land, and it will create however many of whatever type of templates that you have. So if you were to download this guy today, and you have templatized and moved your app into Cube already, you take your template, you feed it into this YAML file, and it will build out your environment exactly as you with your application. What we've done is take some of the examples from Kubernetes and make them and put them into this repo. So I mentioned they're controversial because Cube doesn't have a concept of templates right now. OpenShift does, and there's other technology, there's probably a dozen other templating technologies out there. But anyway, so we're porting as many as we can, and we like to build up a pretty big corpus of other applications that we could throw at these environments. These configs can also include a persistent volume. They can get as complicated as you want. It could be as simple as a pause pod, if you're familiar with that, or it could be as complex as a multi-tiered application that includes persistent storage. And in fact, those are the ones that we've got here. So the Redis example, the guestbook example with persistent backend storage in a database. And it will also set up all of the routing and secrets and build configs, et cetera. So that's what we did on the CNCF cluster. So maybe it'll make a little bit more sense if I show you what it is. Okay, so in this scenario, what we found with OpenShift version 2 was that, this is not Kubernetes version of OpenShift 2, the previous version, which had our own implementation of containers. We found that flooding the API server was not a good idea. So we've got these control loops and backoffs and delays that are built into it. In this scenario, I'm not doing a tremendous amount of load on the system, so I don't really need those in there, but that's what they're for. So, and then this config is pluggable as if, you can put whatever applications you want in here. So in this scenario, just Nginx, Guestbook, Elasticsearch, et cetera. And we're only going to do one of each. So there'll be one namespace with one of each of these applications running in it. So I've just right now got kind of the normal Kubernetes stuff in here. So I'll go ahead and run this horrendous command. There's not really much to it. Make it verbose, use the cluster loader portion of the ETE test. So the ETE test has like 400 plus tests in it. We only want to run the cluster loader portion of it. And then we use Viper for it. This is written by a coworker of mine named Sebastian Hug. And so it uses Viper, and then you point it at a config file. The idea is this config file could represent your environment. So it's going through and creating all these containers. Incidentally, the images are preloaded, like they're in the Docker already. So not terribly sexy, but it did do it. Everything's running. And the idea here is that when we were on the CNCF lab, we would increase those integers and be able to scale out as wide as we as wide as we wanted to, as wide as the hardware and software is capable of doing. So the single test harness can do, as much scale as you might want. So pretty simple demo, but we're hopeful that we can find a way to get that upstream into Kubernetes so that you guys can. Right now it's on GitHub and it's in Python, but we're going to try and get it into upstream Kube proper. And contribute back to the community. So, any questions about that utility? Does anyone think they could make use of it? Yeah. Okay. Anyway, so that's what it is. So what did we learn? We fired the cluster loader at this big OpenShift environment. What were some of the takeaways? Well, this is our config that we ended up with. We ended up with 1,000 nodes, 13,000 tenants or projects, whatever, 52,000 pods, and all these other objects were loaded into etcd. Incidentally, we plan to go a lot higher, but we did hit a bug in the API server that had very recently been filed upstream at the time. So the API server was crashing, and at that time, our time was up on the CNCF lab, so we didn't get a chance to continue, but we'll do that at bigger scale the next time we get on that gear. So, a couple things we found. A lot of our team's output is actually capacity planning information, and that gets into our product documentation. So, probably the initial conversation that we have with customers is, how much gear do I need to buy, or how much cloud resources do I need to provision? And so we create these formulas based on our actual tests that they can use to extrapolate and decide how much gear they need. In the scenario on the left, we found that loading all of that stuff that I just showed you into etcd takes a fair amount of space on disk, more than we had originally documented. And so we've gone ahead and updated that documentation and used this as justification to say, look, you need to give 40 gigs to etcd if you're going to do anything at scale. Fortunately, etcd is really easy to move. It's got just that one database file. So like MySQL, you can just ship them around if you can handle an outage. But if you want to size everything accurately up front, that's the value out of some of these tests in terms of etcd and disk. Incidentally, this is etcd version 2, in case you were curious. And on the right-hand side, we've got some other Grafana graphs. I think the only interesting part about this is that you notice this drop-off in CPU, and that's actually when the API server fell over. And luckily, like I said, that bug had been fixed. So, and this is an alpha version of OpenShift 3.3, so this bug never shipped in the product. Question? Okay. Yeah. OpenShift's installer is is written in Ansible, which is incredibly flexible, totally parallelized, and not really sure how we would survive without it. So we also use Ansible for every other thing in the world. One thing we noticed is that when you're gathering, so Ansible will go out to each node, gather what it calls facts about that node, and then suck them back over the network and hash them in memory. What happens is when it does that hashing across thousands of nodes, you get a tremendous amount of CPU utilization, which you need to know about because if you run out of CPU, sometimes those install portions could fail. And so we worked with the Ansible guys to optimize the crap out of that part. And we can actually shove those results into a database at this point instead of having them in a flat file. So it's a little bit more optimal. Just SQL light, but actually helps this performance problem significantly. And again, this is just the installer if you're doing it at a huge scale.
Yeah, you're running the Ansible against the virtual machines or
yeah.
against the hypervisor?
Against the virtual machines. Yeah. So, I guess we can start talking about that. So that was the end of the performance tests for CNCF. Did that all make sense? Was there any questions? Do you think you can use some of that information?
I'm curious if you hit, was Nova involved in the performance of your deployment, or did you pre-deploy all of the VMs and then come back and lay OpenShift?
Yeah, right. So we ran into, when we did the initial OpenStack deployment, we used Swift, and which we regretted. But in the next iteration, we're already using Ceph, boot from volumes with snapshots. So we expect that we had a problem with Nova that it just took forever to blow out these 1,000 VMs. And so we're trying to optimize that. And so for our next strobe, our next runs, we'll have those optimized. We won't have to keep the VMs around. We'll be able to whack them the same like we uninstall OpenShift.
So there was a Nova scheduler limitation of some kind?
It wasn't the scheduler. It was just pushing all the images around. Yeah. Just shipping those images around on disk to 300 nodes just took a long time. So it was like an hour just of shipping images around, and then the install actually kicked off. Was there another question?
Yeah. So in the scalability talk I went to yesterday, they were very explicit about what they meant by scale is it works within certain latency bounds, both the API calls and for things to get done asynchronously later.
Yeah.
Was that part of your methodology here?
That's specifically about the density test that's in ETE. So that's what those definitions apply to OpenShift as well. We take Kubernetes as is. We add a couple things that aren't yet upstream, but are going upstream. Things like, for a while, the security policies weren't upstream. We were using them. But my point is that those SLAs are part of all of this testing. Yes?
Okay. So the second part of my question is that when my colleagues do some tests, they're interested not only in how far can you scale, but once you start breaking your time bounds, you want to break down so you can find out what part of the system is failing. Are you collecting breakdowns of this subcomponent?
Yeah. So it's not in this deck, but our team has built a tool called pbench, which is a distributed system analysis tool, and it'll gather all of the CPU profiles like Go pprof data. And so we have that for every run we do across all of the important nodes on the system have full tracing enabled. We have all this graphs and stuff. So I showed you a Grafana graph of CPU. That's one example of that. But there's also pprof data, and those are the ones where we, like Tim and other guys on OpenShift team would go in and optimize code paths or algorithms in Kubernetes code to help with scale.
So the kind of thing I was talking about is, say, the latency to do an API request, it actually goes over warranty thing. To get the things fully set up asynchronously, there's several steps that have to be taken for each one, right?
So I think the open tracing guys could probably play a role here, because the events that Cube throws are probably not as granular as we need, and they're also, the timestamps aren't accurate enough. So there's improvement to be done there. What I find personally, and feel free to disagree, is that the only thing that matters is the user experience, is how long, like, ultimately we want to know along the way how long each subsection took. But we want to make sure that the total time to stand up a pod is within those 5-second bounds as well, with pre-pulled images. And at scale, it turns out that you end up violating those around the 60,000 pod range or something like that. So, and a lot of this is subjective. It depends on your I/O subsystem performance.
Well, that's the point, is
yep.
at the end of the day, you only care about the total result, but in order to make it better,
yep.
you have to find out what piece is taking too long.
Absolutely. And so every time we do one of these runs, the actual activity is analyzing all of the data that gets recorded out of it and finding out where we CPU bound. In that Ansible scenario, I actually showed you the good graph. The bad graph was a disaster. And we fixed all of those bugs in Ansible along the way. But those graphs were instrumental in telling us what portion of the Ansible playbooks actually had those kinds of issues. So in the Ansible scenario, that's one thing. And then the other thing is, in the API server, we might see huge CPU spikes, and then we can go in and look at the pprof data that correlates with that time frame and get backtraces, basically, that tells us how much CPU time was spent in a certain function or whatever. And then it's just like you peeling an onion. So we do have like extensive debug and tracing in all of these runs.
Yeah, I guess the concern that I'm bringing here is it's one thing with utilization of resources, but there's a class of bug of like excessive locking in someone where you find it takes a long time, but no resources have been intended.
Yeah.
So just looking for intended resources is not going to find any problems.
I would agree with that. I mean, I would say that there's enough low-hanging fruit, actually, is really what it comes down to. There's also other teams that are working on locking scenarios in the Go language itself that we need to improve. Like, the fact is, Go is new. It doesn't have ideal tracing facilities right now. And there's some pretty big I don't want to say showstoppers, but we wish it would be C, basically, and that we could debug it like a normal language. But here nor there, we have everything in Go at this point. I was going to run through a couple of tuning subsystems. Yeah, yep.
Sorry, a couple other questions. So I'm curious about the network topology. If you're running Red Hat OpenStack, I'm assuming you're using triple O, single NIC on VLANs, and I'm assuming a flat divided network potentially for the
Yes. Yes.
What about the physical network topology?
It was a single switch with a single 10 gig drop to every node and a flat VLAN. If you're talking about VXLAN?
No, I'm talking about the physical network topology. It wasn't
No, single NIC. And actually, visibility into the networking tier is something we specifically asked the CNCF to give us. So they were managing the hardware. We ran into like firmware issues on the NICs. We ran into a bunch of ugly shit before we could even get OpenStack installed. And that was specific to that lab. So when they bring more gear on, we're going to have to probably go through the same thing. But and we know that wasn't optimal. We did do the double VXLAN encapsulation here. The next time we go through, we will use flannel. One of the things we like about OpenShift is it has multi-tenant secure networking out of the box. We need OVS to do that. If we drop back to flannel, the trade-off is you don't get that multi-tenant security anymore. Depends on the site whether or not that matters. Or another pluggable network implementation. So that's another thing. We work with all these partners and vendors, and the load balancer is pluggable. The networking subsystem is pluggable as well, totally pluggable. And it's fully supported. So thanks for bringing that up. The networking performance is really important to me, too. That's where I kind of came from in my history. Anyway, so for CPU-bound workloads, in Cube 1.3, one of the main features that went in, and I guess this is really all you need to know about performance management on Cube, is that there's a quality of service tiers that have been enabled. And so there's what is it? Batch, best effort, guaranteed, and I think there's a third one, batch, I think. And the idea there is that if there's a contended resource, the guaranteed pod would get scheduled and run on the CPUs more often than the best effort pod. The idea there is to increase utilization and also have some relative priorities between pods that are running on the same system. So if you have a performance sensitive workload, you would want to place that in the guaranteed tier. That's really the only takeaway. You also want to make sure that there's a limits and requests capabilities in Kubernetes as well. You want to make sure that those are sized to fit your application. A lot of times people will undersize it and wonder why things are running slow, and the reality is they're being throttled by the design of the system. So for a lot of these scenarios, we'll turn off those or make everything guaranteed, or set no limits on the pod spec. Other applications might need specific CPU features or run on specific cores, and there's kind of weird ways that you can manage this now with labels on nodes and upcoming features like taints and tolerations. So eventually, we'd like to get to a place where you have a little bit more fine-grained control over where things run, NUMA topology, PCI, locality, et cetera. We don't know if that's going to be manageable or not, but it is something we're throwing around the ideas for. Memory latency, again, is around NUMA and limits. I did have a slide here about networking. So a lot of this is it's totally infrastructure dependent. If you're running on Google's cloud, you have their SDN. If you're running on Amazon, you have their SDN. If you're running on OpenStack, you have that SDN, et cetera. Each one of those has their own characteristics in terms of scale, throughput, and packets per second type latency numbers. We've found that running on public clouds we basically cannot do successful regression testing on public clouds because there's too much variance. And this is something we're in constant struggles with because they're extremely popular, the public clouds, but we have too much noisy neighbor problems. And also buying the amount of resources it takes to actually get huge guests that have all the provisioned IOPS that you might want, and in these placement groups or equivalent technologies on different clouds, the budget just runs right through the roof. So we've fallen back to bare metal because performance analysis needs that tight control. And if you don't have it, then you end up chasing red herrings all over the place, and it's a waste of time. For storage, Red Hat and I think Google have introduced something called storage classes, which is a way of tiering your storage. So you could say, some people may already have slow SATA disks in their data center, and they've got other workloads, databases, whatever, that need NVMe disks. And so you've got this tiering concept already in your data center, most likely. Bringing that to Cube with something called storage classes. And you have gold, silver, and bronze. And the more critical workloads have the gold tier of storage, which is analogous to the quaz tiers of CPU and memory that I just mentioned, guaranteed, best effort, et cetera. So there's a blog up on Kubernetes from last month about that one if you want to read more. Any questions about all that stuff? Yeah.
Correct me if I'm wrong, I saw mostly long-lived containers, long-lived container processes and measuring their performance. Did you or will you be looking at short-lived containers?
Yeah, I mean, the build farm is the short-lived container case for us. Those containers usually live 1 minute, but it's not like functions as a service where things run for a couple hundred milliseconds. That's not the type of thing we're looking at yet. But the build farm analysis was very high churn. And in that scenario, I think the use case is going to be Kubernetes scheduler throughput and doing something better than increasing the parallelism that's possible with Docker. We thought about having multiple Docker daemons to kind of parallelize things, but the reality is it's not highly parallel. I would call it mildly parallel safe at the moment. But you can run into situations, and until Docker 1.12, if you overwhelm the Docker daemon, you are screwed. All your apps are going down. Things are much better with 1.12, where if the daemon's not the parent anymore. So if you kill the daemon, you don't actually lose your apps. But the short-lived containers is the build farm scenario I shared earlier.
Did you have, sorry to belabor this, mount and unmount times? Because you were using block storage from the containers. Was there any contention about mounting, well, you said you were using Swift, so.
Swift was for the OpenStack VM storage. So the mount and unmount times they're in there. I mean, yeah, we had It's actually not that big of a deal. It actually takes more time to allocate a VETH than a block device, quite honestly. I mean, we're using Device Mapper for our storage here, but overlay is one scenario we investigated. We did some tricks recently. It's like overlay would get us faster storage, faster graph driver because it has memory page cache sharing, and so you have less memory usage. And it also doesn't allocate a kernel device, so you don't go through those code paths as well. But basically, we started using Device Mapper with a little bit of a bind mount trick to get rid of both of those scenarios and still deliver POSIX compliance. So there's a blog on that up as on developerblog.redhat.com. So what are we going to do next? The gentleman asked about the normal density API response time latencies. We need to work on, hopefully, in the next couple of releases of Cube, we need to formalize that a little bit more and extend it. Some of my ideas, if I was just spitballing, is we need to know like CPI kind of measurements around all of the subsystems that are involved. We need to actually test real applications and run workloads on them. So if you grab our Git repository, we also have a workload generator that spins, so it will deploy all the apps with cluster loader, then it will come back and spin up a dynamic number of JMeter pods and fire off the test against those. And it will go and query the API server for the routes. And it will build a JMeter test plan dynamically and then fire load at it and then build graphs. So all that's in there. I would love to see something like that added. And then, of course, we want to make sure that it's actually tested against a full HA environment if possible, which means multi-master, multi-etcd, et cetera. I think that's pretty much it. And we have some etcd testing, of course, that's always ongoing. Oh, and another thing is hyperconverged storage. So Red Hat sells a product called Container Native Storage, which is Gluster, and it's running on top of OpenShift or on top of Kubernetes. And it provides the dynamic provisioning of persistent volumes directly to Kubernetes, and it runs within Kubernetes as pods itself. So that's something we're going to take a look at over the next couple weeks. The guys are extremely busy with features, and I know Connor is here. He's doing this one, pod level C groups, Red Hat. I mean, it's not about the individual people, but the idea is we're tackling many, many different things. Huge page support for certain applications. We've also introduced certain sys controls, the ones that are namespace aware. We've introduced already in Kubernetes, the Quaz stuff. And then another thing we're probably going to need is a way to feed hardware features into the scheduler. At least this is my opinion. So you can schedule against certain hardware resources like GPUs or FPGAs or whatever. So heard clapping from the room next door. Must mean I'm over time. Hopefully that was helpful to you guys. Questions? Any last questions? Yes?
You mentioned your someplace where this is all your AMI configuration, and I would assume there's something there for your collecting sampling intervals and all the plugins that you have installed. Where's all that information?
It's on our GitHub. So it's github/OpenShift/SVT. And again, these slides will go on SlideShare and Twitter in a half an hour or something. Okay. Anything else? Yes?
Yeah. What's the best way for people to get involved?
In this testing? Or
just finding, outstanding issues that need help?
Yeah, so let me do one thing. SigScale is the place to go for information about all of this stuff. SigScale, SIG scheduling, and SigNode. If you're not participating in a Kubernetes SIG and you want to get into this stuff, I would highly recommend you go there. In terms of the issues here, we're kind of slowly socializing the full list of stuff that we want to add to Kubernetes. And so it's all sort of internal information now, but we're going to slowly start publicizing that stuff. And that's actually what this conference is about, is making those connections. So, cool. Thanks, everybody.